Hi everybody, welcome to another video in Math 1324, section 2.5, exponential functions. The focus for this section is just to prepare for the next section. The section 2.6 is more important and will be covered in much longer time. And also, major application for exponential function will be in chapter 3. So with that said, section 2.5 will be a very quick section. Exponential function. So we define exponential function to be b to the x, where b is the base, and the base cannot be negative, cannot be 1, cannot be 0. So we define that to be greater than 0 and not equal to 1. That's called exponential function, and we call the base b. So this is exponential function base b. Right. Now some properties of exponents. When b is positive and not equal to 1, I have the following. Anything to 0 power is 1. Of course, anything, satisfy this condition. B to the first power is itself. Anything to the first power itself. When we have negative exponent, we turn that to 1, bring that to the bottom, turn to positive. So there's a saying in this case, says cross the line change the sign. So we cross the division line from the bottom to the top, or top to the bottom, we change the sign. Let's look at some example. Let's say we have 2m to the negative 5 over 3n square, for example. If that is the case, we move that m to the negative 5 to the bottom, and we become positive exponent. So it's like that. Or if we have a negative from the bottom, we move to the top, it's going to be positive. So cross the division line, change the sign of the exponent. Next we have this in 1325, that is more important, but for now, if we raise to a rational exponent, the top will be the power, the bottom will be index of the radical. So let me write this. Say m is a power is on the top, the n is the root, and the root is at the bottom. Root is at the bottom. Right. So let's look at one example. If we have x to the 3/2, that means the 3 at the top will be the power, the 2 at the bottom will be the root. So that's what we have. And of course, the square root, we don't really need to write the 2 there, so we just say that square root of cube. Right. The next three are also important when we multiply. Now this is very important, essentially in the next section. A product turn into a sum. Keep that in mind. Quotient into a difference, and power to power, exponent to another exponent, we multiply the exponents. Right. So these three will be very important in the next section. Right. Let's look at some example. Now we sketch, and always sketching is just find the points, connect the point, not connect, but try to find a curve on the line that go to all the points as best we can. We'll just choose some x values and then find the y values. Right, let's do some values for like -2, -1, 0, 1, and 2. Right, now substitute this into x. 2 to -2. So we said negative exponent move to the bottom, turn to positive. That would be 1/4. 2 to -1. 1/2. Negative exponent move to the bottom. 2 to the first is 2, so 1/2. By definition, anything raised to 0 power is 1. Anything raised to the first power is itself. 2 square will be 4. One thing to note that because of the way we define this, x doesn't matter what it is, negative or positive, it is always defined. So one thing we see later is the domain of this is all real numbers. But that for the next section, the next part of the section. Right, so we just plot the points here. -2, 1/4, about here. -1, 1/2. 0 and 1. 1 and 2. 2 and 4. So if we connect them, we have the graph of exponential function 2 to the x power. Right, let's try that again for y to the 1/2 to the x power. Right, the 1/2, so I write a little more space for that a fraction. Right. Again, I choose some easy number to evaluate. So we have to the top, to the bottom. So we have a fraction to the power. So that power goes to the top, goes to the bottom. So now we negative exponent, cross the line, change the sign, move that to the bottom, change to positive. Move that to the top, change to positive. 2 squared, so we 4/1, which is 4. (1/2) to the -1. Power goes to the top, go to the bottom. Now cross the line, change the sign. Anything to 0 power is 1. Anything to the first power is itself. And now we have the square. So that power go to the top, go to the bottom. Right, so you have the points. Now plot all the points here. -2, 4, -1, 2, 0, 1, and 1 is 1/2. 2, 1/4. that is y to the 1/2 the x power. Right. Right. So next we study the properties of exponential function. So a few things here, because b anything raised to 0 power is 1, so the graph always go to the point 0 and 1. And then we talk about the domain. Doesn't matter what the x is, positive, negative, 0, it's always defined. So domain is all real numbers, and we keep that in mind. But regardless of the exponent, we see that we only have positive number. If we have positive number as the base, when it raised to any power, it's going to be positive. It's going to be positive. So we have the domain and range. The graph always go to the point, and it's always positive. And because it's positive, but it gets very close to it. So we do have the horizontal asymptote at the x-axis, or y equal to 0 is the horizontal asymptote. Domain is everything, all real numbers. The range, all positive numbers. And then there's two cases. When it's bigger than 1, in this case 2, it's going up. When it's less than 1, it's going down, decreasing. So that's why we have be bigger than 1, increasing, less than 1, decreasing. Right, so that we summarize everything in this. So the two important parts of the graph is it goes to the point, and it has the horizontal asymptote of the x-axis. Domain and range is this. Right. Next we define the exponential number, exponential natural number e. So e is defined to be this as n go to infinity. So that e is equal to 2.71828. On your calculator, the e will be second divine. Or if we have particular, we have e to the power second ln, that e to a particular number. Any exponent, let's say e cubed. So there. Alright. Now we go to one application which we'll spend the whole chapter 3 talking about it, compound interest. So if a principal or the present values is invested at the rate r, compounded m times a year, then the amount of future values at the end of t years is given by this. Right, so we have the present values, the principal or present value is what we call the investment, or a loan, or something we put in the bank, or something we take out from the bank to borrow money, or a loan or an investment. And then after a period of time, it's going to be equal to a future values. And now we're interested in the future values. I said we'll talk about the whole thing in details in chapter 3. Now we just focus on we have an investment. After a period of time, it will generate some interest with that amount, original amount we have, what we call the future values. Right. So we'll be given by this. So when m is the number of time it is compounded in a year, and if m go to infinity, we have continuously compound interest be given by this. So we have two formulas like that. So here's an example. Suppose $1,000 is invested in an account that pay 6% interest. So usually when we say interest like that, that is the interest for the whole year. And find the values after 5 years. If it is interested, if the interest is compounded annually, quarterly, and so on. Right. So the few things here. T is the time in years, and m is the number of times it is compounded a year, and r is the rate for the whole year. Right, so in this case, let's write out what we have. So this is an investment, so that is the original amount or the present value. 6%, that would be the rate, and set as decimal, so 0.006, and after 5 years, so that is t, and as is find the future value, so we don't know a. Also this problem we don't know m, because if we use that formula we need m, right? So but m is the number of compounding period a year, so how many times it is compounded in a year. So for the first part, annually, meaning that it is compounded 1 time a year. So with that, straightforward, we have the formula. $1,000 plus the rate, m is 1 over m times t, 1 times 5 years. Right, so we have that. So we have 1,000 times 1 plus, we can just, of course 0.6 divided by 1, we really don't need to do that, but do that for a reason, and then the time will be 1 times 5. Again, we don't need to times multiply by 1 or divide by 1. So we have that. Right, so that's it. This is money, so I write like that. We round to the pennies. Right, next, quarterly. If the interest is compounded quarterly, that means it's going to be 4 times a year. Of course, you can enter from the beginning. Once again, if you have alpha equal, and if you have a fraction, that would be nice, enter as is. If you cannot do that, just divide. And then raise to the power. It would be nice if we have that. If not, we just have to use the old form, the hat, and then we, in parentheses, we say 4 times 5. We'll just put 20. Next monthly, that will be 12 times a year, so m is 12. of course you can enter the same thing, but if you have this calculator you can just highlight it. Remember, and I should enter this for a reason. All we need to do here is just change to 12, and here we have 12 times 5 or 60, so that and daily is let's just say it, a regular year of 365 days. Of course, if it is a leap year like this year, it's going to be 366, but generic, let's say 350, 365 days in a year. Again, just highlight, copy and paste. If you don't want to do that, you see there's the entry here, so second and enter, that the last entry, or second enter again, that would be the entry before that, and second enter, so entry before that. So just give second enter to find the previous entry, or if you can highlight it, hit enter, copy and paste. You have 365 days. You have 365 times 5. So have that. Right. Next, continuously. Continuously, that is where we use this formula. So that means as the number of compounded period a year increase. So in this case, if we say that go to infinity, but we use completely different formulas when it is continuously. The rate, the times 5 years, so 1000 times e to the power of 0.06 times 5. So that gives us 86. Right. So you see that more and more period it is compounded, the more money we generate. But we cannot generate more than this. So continuously is the most you can generate money at a fixed rate. So of course that is where m go to infinity. I just want to show you this. So when we take m to be a very big number, let's say it, we have a very big number like 1, 2, 3, 4, 5, 6, that's 1 million. Let's say it is compounded 1 million a year. It will raise to 1, 2, 3, 4, 5, 6 times 5. And you see, it gets very close to this. So when m go to infinity, we have the different formula, continuously compound interest, and that's what we have. Like I said, we spend the whole chapter 3 talking about the interest and other things, so we'll focus more on this. Also, at the next section, we'll have more on this as well. But anyway, I'll stop this video here. As always, thank you for watching, and see you in another video in Math Tech June 24.